All right, so on our last set of notes, our last PowerPoint, we talked about how to go about testing our assumptions, kind of really focusing on, I guess, the 3 out of 4, right? Focusing on how to assess whether the normality assumption is satisfied, homogeneity of variance assumption, and we talked a little bit about the independence assumption. We talked about this example in terms of like our serial data set. And right, we got lucky. It turns out our serial data set looked pretty good. So we were done. However, right, an important question would be, well, what if there had been problems in our serial data set? That is, maybe in a homework assignment, maybe in a lab, you come across some situation where the assumptions are violated, maybe in a take-home test. What would you do in a situation like that? That's what we're going to talk about in this somewhat shorter set of PowerPoints. Now, I mean, there's a lot of solutions to what we would do. Of course, like the more sort of complicated, the more sophisticated, right? The more maybe effective they are. We're going to focus on one very general but very powerful solution. And that is the transformation of the dependent variable. That is the transformation of the y variable. It might seem a little bit like magic, but you certainly can prove, and there is convincing underlying theory as to kind of why this works and exactly the type of situations in which it does work. So you can prove and show this mathematically, but it's a little tough to do. It's beyond the scope of this class, so we in 512 will just kind of have to take it on faith that we can often fix these broken assumptions by doing a transformation on the y variable. These transformations can stabilize the variance. They can normalize the distribution. Sometimes, in fact, often they do both at once. Now, the downside is what? The downside is that these transformations can hurt the interpretability of the model, right? So, right, they kind of help us on the sort of technical and very important side, right? I mean, there's nothing more important than making sure our assumptions are satisfied. Sure, if our assumptions aren't satisfied, SAS will run a model, but the numbers we're getting are distorted and deceptive and sort of not justified. And right, in some ways, garbage. So at least with a transformation, we're getting numbers that are justified, that are valid. It's just they're sort of tougher to work with and tougher to interpret and tougher to apply to the original context of our problem. Now, when I talk about transformations, what do I mean, right? Well, probably the most common transformation is the log, and when I say log, we usually do the natural log. So the natural log is a very, very common transformation. It works well with large residuals in absolute, when large residuals in absolute value are associated with large predicted values. So that's kind of maybe the funneling pattern that we observed in that simulated data set before. Sometimes the log transformation could be overkill. That is, like, it might actually take like a funneling pattern and smush it so much that it kind of creates like the opposite looking funneling pattern. So it's a powerful transformation, sometimes too powerful. A slightly less powerful version of the log is the square root transformation. So square root transformation kind of works in the same way. It's useful in situations where larger residuals are associated with larger predicted values. Doesn't work quite as strongly as the other one, sometimes good, sometimes bad. So in practice, we might try both the log and the square root and see which one of the two works better. Now, if we have the opposite looking funneling pattern or the opposite situation where large residuals are associated with small predicted values, then we might square our y variable, right? Instead of working with y, we work with y squared. Now, an important takeaway. After we actually complete or do a transformation, we must recheck all of our diagnostics and make sure that those originally violated assumptions have now been fixed. We don't just take a transformation like slapping on a band-aid and say we're done. It's not that easy. We have to go back to those scatter plots, to those histograms, and make sure that this transformation did in fact what we wanted it to do. Which means that good model building is this sort of iterative, cyclical process. So we run our diagnostics, it doesn't look good, we do a transformation, we run our diagnostics again. Maybe it looks better but not great, so we try a different transformation, run our diagnostics again, compare the results. And again, always remember the transformation when you try to do interpretations. Right? So imagine we did a log transformation on the weight of bears. And we want to interpret, maybe we did like a simple linear regression, just weight or log weight as a function of, say, neck girth. So how would we interpret that regression coefficient? That regression coefficient is basically, right, for maybe it's like, maybe the regression coefficient is 3. So what does that mean? It means that for a 1 unit increase in neck girth, we expect the log of the weight of a bear to increase by 3 pounds. Which is a little bit less useful, right? Because what's log weight? What's a log pound? What does it mean for a log pound to increase by 3, right? Those are not really like easily intuitively grasped ideas. So we lost a little something. In general, this is sort of what we lose and what we can preserve. Right, you cannot reverse transform regression coefficients. That's just a sad and unfortunate math fact. That is, right, you can't take that coefficient of 3 that I had before and then just do the opposite of the log transformation. What's the opposite of the log transformation? It's the exponential operation, right? You can't just take the number 3 and calculate e to the number 3, and then that's how much we expect the weight to increase by. It just doesn't work that way. We cannot reverse transform confidence intervals for the mean. However, we can reverse transform predicted values. So that's good. So, right, we can still do useful predicted values in the original units of the problem. And we can, right, we're theoretically justified in reversing the transformation of prediction intervals. All right, so as an example, imagine that we had to take the natural log of weight to properly fit our bear data set. When generating a prediction for a neck girth of 30 inches, say we get the value 5.7. Remember, this is saying that for a neck girth of 30 inches, we expect the log weight of a bear to be 5.7. If we wanted the actual weight, we could find that by exponentiating 5.7. And I'll leave it to you to plug that into a calculator and verify that e to the 5.7 is in fact 300, right? So we would say that a neck girth of 30 inches is associated with an expected weight of 300 pounds. Right, and when we're talking about prediction intervals, right, a prediction interval is just an interval that has 2 endpoints, right, a lower endpoint and an upper endpoint. And same idea, we could exponentiate both of those endpoints, and that would give us a prediction interval in terms of the actual weight, in terms of actual pounds, in terms of our original units. Now, I said that this transformation can fix violations of normality. I said it can fix violations of homogeneity of variance. I did not say it could fix independence. So what do we do if there is violations of independence? Well, unfortunately, there's not an easy fix. How you fix dependency problems depends very heavily on the type of dependency that you run into. And typically they require almost like an entire class to really talk about and develop the notation, the tools, strategies, the algorithms, the techniques to accomplish it. Violations of dependency are really rough. Regression is not robust in terms of violation of dependency. That is, even somewhat minor violations of independence can have important harmful impact on your model. And unfortunately, it's not easily fixed. So how do you fix violations of dependency? You have to learn more. And it's going to depend on the context of the problem. I talked in a previous slide about the context of time series analysis. We offer an entire class on time series analysis. So if you want to solve that problem, you have to learn more. If you have a clinical trial and you're giving someone a drug and you're measuring maybe their cholesterol at different time points, we have a dependency problem, right? That is, a person's cholesterol at today probably depends on what it was yesterday. This is a little different than time series, because in time series we usually have a single time point, that is maybe just like one stock, whereas in the clinical trial I was talking about, we might have hundreds of patients. So that creates a different situation. That's referred to as longitudinal analysis. And again, that is a whole class in and of itself. We offer a whole elective class, typically taught by the great Professor Gallup, on how to handle longitudinal analysis. So, unfortunately, violation of dependency requires a lot of extra knowledge. It's not something I can just slide into a couple slides. All right, so at this point, we're pretty much done. We just have one more set of slides to finish up our weekly discussion of diagnostics. The last topic we have to talk about is the very important topic of collinearity. So take a little break, and I'll see you soon.